Hello everyone, welcome to lesson number 3 of intermediate OpenCV tutorial series. And here, the first thing we want to do is clone this repository by running this command over here. It will clone the repository, all the images that we need for this project. So once everything is done, go back and open this table of contents and go under the lesson number 3 shape detection. That is what we are going to work on today. So let's start the project by first importing all the libraries that we need. We need OpenCV, we need NumPy, which will import as NumPy NP, and we also need the Colab version for cv2_imshow. We'll use Google colab.patches import cv2_imshow. So this function imshow is just for displaying the images for us. Let me increase this a little bit so it's easy for you to see. We will also make it full screen so we can clearly see what's going on. So we have the shape detection and we are just specifying all these libraries right here. The first thing is let's read the image. And the image is inside this folder OpenCV images and shapes.png. So this is the image that we are interested in today, and we'll do that by reading this image for us. So we'll say OpenCV, please read an image and save it under this variable called img, and you want to use OpenCV's imread function. And this function just needs the name of the file name and the file path wherever it is located. So it's located inside the images folder in the directory, and we call it as shapes.png. So this will just read the image for us. We can always test the image whether or not it read the right image by using the cv2imshow function, and we just run this and we see there is an error right here. So it looks like we missed something. Google Colab patches from, so we need to import from Google Colab patches import cv2_imshow. No worries, we fixed it. Now we can just simply rerun this and we can see that it's able to read the image and it's displaying it here for us. So good. Now, the first thing you want to do, since we're doing shape detection, we want to discuss and identify what kind of shape it is. So we know, from a human eye, that this one is a circle, this is a hexagon, this one right here is a square, this is right here a triangle. So we, from a human perspective, we know what these images are. But if you were going to give this control to a computer program, how would the computer read through all these colors and identify these images? So of course we need some sort of algorithms in order to do this, and we'll see how we can do that. So we'll try to read these shapes and images through OpenCV or image processing perspective. So the first thing you want to do is convert this into a grayscale image, and we'll use OpenCV function convert color. So convert color, CVT color. This is just going to convert the color from whatever color we want to whatever color profile we want. So you need to specify the image that you want to convert this to. So img is the original image, and we also need to specify what kind of conversion we are doing. So we are going to convert from color to grayscale. So we're going to use CVT color BGR to gray. You have BGR to gray, and this color profile is just going to convert the colorful image into a grayscale image. We can always use the cv2imshow function to see what kind of an output we get, and you can see that it's already converted all the colors into a grayscale profile. It does have the shape and the boundaries of the image, but it's all grayscale. Okay, so we have the grayscale image now. Now, the next thing we want to do is understand some of these functions, some of these images, some of these values in a more clearer way. And for that purpose, we'll use OpenCV's thresholding function. This thresholding function is responsible for converting anything that you are interested in, anything that your profile is interested in, into white, and then the rest into black in color. So this is basically a filter, and you can say, hey, okay, OpenCV, anything which is light, like this hexagon, this circle, the square, the triangle, these are all lighter colors compared to the background, which is black. So anything which is light, please make that into white in color, and everything else black. So I'm not interested in them. I'm only interested in the white in color profile. For that purpose, we use OpenCV's thresholding function, and we'll call, hey, threshold, use this OpenCV function called threshold. This threshold function is a built-in function from OpenCV which can take the source and threshold value and the filters and then convert that into a black and white image. So it basically filters the image to the values that you are interested in. So you specify the image, which is our grayscale image. Now you want to specify the threshold values. So we'll say, okay, anything which is between 50 to 255. Because we know white color is 255, so anything which is 255, and 50 is the lower end, and we'll see 50 should be okay in our case. And we are also specifying the type, which is not too much of an issue. We just specify 1 and we take care of this. Now let's see if we can display this image here for us. So CV2 I am show thresh. So let's see how this kind of an image looks like. And you can see that it's already converted everything into black and white. And yes, it's everything that we are interested in. It's all, you know, converted into one color, and the background is in another different color. So this thresholding function has already used a filter, and everything that we are interested in, it has specified them into one color and the background into another color. So that's the purpose of thresholding. So it's converting that into two different values, and now we can use that to our advantage. So now we have all the functions that we are interested in. We have all the images that we are interested in. Now let's start reading these different values from an OpenCV perspective. So OpenCV has a good function called as find contours. So this find contours function is a type of function that's able to go through all these images and go through this right here. You can see the circle, and it'll find all the contour, the outer contour, which differentiates these two colors. The black color and the white color, these are differentiated by this circle right here, and it will find that contour which is differentiating these two colors. So these two color pixel values that are being changed or being differentiated, it will identify the border of these pixels. So we'll use this function called contours, and these are just the H, and this thing is nothing but just specifying the history and the flag values. So we're not interested in that. We're just interested in the contours and the threshold. So CV2 find contours, and contours is given by contours. So you're just specifying the different types of contours that we are looking into, and we are specifying, okay, the contour should be taken out from the threshold image, and you're also going to specify what kind of contours you're interested in. And this is of course a binary image, since we use the threshold function, and we are now you're going to use different types of filter and pixel values. So you're saying, okay, it's going to be between 1 and 2, and right now you don't need to understand, you know, these two values. It's as long as you're putting 1 and 2, it'll work fine. You don't need to worry about why and not. So let's go into understanding what these contours are. So these contours are just specifying all these outer boundary of the pixel value of the shapes. And when we have the contours detected, these contours are specifying information about the circle, this hexagon, the square, and the triangle. So it has information, it has the contours for all these shapes that we see here. And we will just loop through all these contours and go through the contours that we are interested in. So we'll say, okay, for cons, which are contours, or the contours, or for a counter, or inside these contours, for a counter, which is, so we're just looping through all the contours one by one by using the for loop, and you want to identify what are the points that are specifying the contours. So these are the points. In case of a circle, there are too many points since it's a circular image, but in case of a hexagon, you can see that there are 6 points that you need in order to define a hexagon. So these we'll use a function called as approximate polydp, which is able to identify the number of coordinates or the number of points that you need in order to define your contour. So whatever shape you're working with, whatever it could be, how many points do you need in order to identify or in order to draw your shape? So we have this function called as approximate polydp, which can give us an approximation of how many points we need in order to define our image or shape. So we have this function's name is approx polydp, and this DP is the DP is actually the name of the person who invented this algorithm, and his first name starts with a D and his last name starts with a P. I believe it's Daniel Pickard, if I'm not mistaken. I'll put it in the I'll put some text here to identify what's the right name of the person. But this approximate poly is able to give out the minimum on the number of points that you need in order to identify your contour. So this approximate poly just needs the information about the contour that we are working with, and it also needs some sort of an epsilon value. This epsilon value is nothing but the error or the amount of error. Oh, you know what? They have the name here. It's Douglas Pecker. So Douglas Pecker is the name of the person who invented this algorithm, and that's why it's called approx poly dp. So this function takes this information called as an epsilon. This epsilon is nothing but the approximation value, or you could take it as an amount of error that you're okay with when you're identifying this function. So it's one of the best ways of identifying, or one of the best ways to denote the function or the epsilon value is by using the arc length. And the arc length, if you multiply it by 0.01, whatever value you get, it will be more or less acceptable for our error purposes. So as for now, just understand we're just converting this. We're just specifying the amount of error that we are okay with. And we say, okay, arc length, and we tell the contour name and true. So let me go this on this side so you can see what's happening. So we specified the contour. We are specifying the epsilon value, which is given by this, and we're just giving by the arc length of that contour. And based on that, now we need to just specify, okay, we are just going to be whether it's a closed curve or an open curve. In our case, all the curves are closed, so we'll just say true for closed. So we are now specifying all the approximate value, and this approximate will be able to read all these contour values and give us the value of the each and every shape. So let's print this. So we'll see what is happening here. So we'll run this, and you can see that it's able to go through all of these, and it's giving us the points for each and every contour. So now let's see. Okay, we have the approximate, which is giving us the coordinates of the shape of the points. And and these are, you can see it's form of an array. It's an array which is going through all of these points and giving us. So if we go through the length of the array, instead of printing the whole array, if we just print the length of an array, you can see that it's giving 4, 6, 3, 16, 4. And I wonder what that is. So let's go back and print this image or read this image for us. cv2 underscore im show and threshold, and just rerun this again. So you can see that this is a shape, and it's giving us 4 points, which probably represents a square, and it's giving us 6 points, which is probably representing the hexagon here, then 3 points for the triangle, and 16 points for the circle, because circle is, you need too many points in order to define a circle. And the last is again 4 points, and these 4 points is nothing but the outer image, the bigger boundary of the image, which it's not visible here since we are the background of the code and this thing is all in white in color, but that's the outer boundary, so it's given by 4 here. So good. Now you are able to differentiate and you're able to identify, okay, approximate is able to give us the length of the coordinates. Not only the length of the coordinate, also specify the coordinates or the points that can define your shape. So you have approximation, and now you're going to say, okay, if the length of approximation, so or we can say, okay, number of points n is equal to len of approximate. So if n is equal to 4, then this is a square. So you are reading a square. So once you have the square written, you can draw the contour across the square. And you have this function called as CV2 draw contours. And this contours function can draw a contour of whatever size or whatever shape you want based on the values that you are interested in. So draw contours using the on the image called IMG, and since we had this image right here, the original image IMG, we will draw the contour on this image. We'll say IMG. Please draw the contour using the contours that we have inside the CNT function, inside the CNT variable. And once we have this, specify where or whatever the size or shape of the contour is. So we'll say 0, the contour index, and the color, which is 255 for our case, and then the thickness, where we're just specifying what kind of contour image or what kind of a thickness it is. So we'll say, okay, for now, we're only detecting the square and drawing the contour across the square and then displaying the image for us. So we'll say CV2 underscore IM show IMG. Okay, we don't need the IM show threshold function. We're just interested in the IMG function, and let's run this. So you can see that it's now fully black in color, and the reason for that purpose is we are not able to read the image. We have already converted that into an image here for us, and we are also drawing the image with the -1, and this -1 has basically drawn it's filled the whole image with the color that we were interested in. And the image, the square, was the big rectangle, the big boundary box of the image, and for that purpose it has colored everything into a black color or blue color value. Now if we were to say, instead of -1, let's say 5, let's see what kind of an output we get. You can see there's a boundary right here which is almost blue in color, and it's specifying that it's a thickness of about 5. If I were to put 50 maybe, let's run this, you can see there's a bigger boundary which is much more visible, and there's also a boundary right across this square box here, and you can see that it has a boundary of about blue color right across the square which is green in color, and also across the big square of the image. Now you have the square. If we were to say, okay, instead of the square, I'm interested in the boundary of the hexagon. Let's run this, and you can see that it's drawn a boundary across the hexagon. So we are using the approximate function. Using the length of the approximate, you can identify whether it's a hexagon or a square or whatever it is. Since we put n is equal to 6, we'll say it's a hexagon, and we'll reduce the thickness of this, say, to maybe 10, and we'll rerun this, and it's able to draw a contour across the hexagon. And it can also write down that, yes, print, this is a hexagon. So this function can now tell us that this is a hexagon. Now once we have this, we'll say we have a hexagon here. So we have a hexagon here. Now it's able to tell us that this is a hexagon. Okay, good. Now let's go through all of these. So if n is equal to, we had the triangle which is given by 3 variables, we'll say, okay, this is a triangle, and we can print triangle. Okay, we found a triangle, and we can also draw the triangle by using the contours function, and on the same image with the contoured value that we found. And here in this case, we will use a different color. We'll say, okay, maybe you can specify the contour index, and we will use a different color. So 0, comma 255 to 0. So it'll be a green color contour for a triangle. And is our triangle blue in color? Yes. So we can use a green color rectangle triangle, and we'll give a thickness of about maybe 3 size. And let's run this and see if we can see a green color boundary across the triangle. So yes, there is a boundary of green color right across the triangle, which is very good. Now, once you have the image, now you're specifying, okay, so LF, if n is anything greater than or n is equal to or 9, so that's basically your circle. So this is a circle, and print, we found a circle. CV2 dot draw contours, circle on the img image function using the contours that we are interested in, and then you're just specifying the index. We'll put it as 0. No worries on that. And then the color profile, so in this case we will maybe use 255. I think this is a pink color. Let's see what kind of an output we get, and let's run this. You can see, oh, it's giving us a yellow color circle boundary right across the circle. So you have everything, just the square is left. So square, we'll say, okay, LF n is equal to 4, which is given by its square. This is a square. We'll say print b on the square. Okay, good. We are also going to draw the function contours img cnt and you're specifying the index. Now you're also specifying the color we want. We'll say 255 comma 255 comma 0 and a thickness of 3 size. Let's run this, and it's giving us some sort of an error because we missed the bracket here. Instead we put it here, so it should be fine now. And yes, you can see there is a boundary right here, and there is a boundary over here as well. So you are specifying, you're able to differentiate all these colors, and it's able to differentiate and see what kind of a shape it is, and you can identify what kind of shapes that we are working with in this particular image. So if we do a quick recap on this, we did quite a bit of things in this lesson. We looked into the thresholding value, so where we can threshold, we can filter the image of a grayscale image into whatever color profiles that you are interested in. And you can also use the find contours function, which can go through the image and find all the different types of contours that are representing the shapes in the image. And then using the approximate polydp, you're able to identify the points, the approximate points that you need in order to draw your contour once again. And once you have the contours, then you go through all of the length of the approximation, and based on the length of the approximation, you're identifying what kind of a contour is it. If it's a if it's a 6 coordinate contour, it's a hexagon. If it's a 3 coordinate contour, then it's a triangle. Similarly, you can identify if it's a circle or a square. So this is basically helping us to identify the different types of shapes from an OpenCV, from an image processing perspective.